Hello guys, and welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easy to understand. Today we're looking at a problem around the idea of the continuity equation and relating that back to thermodynamics to apply the first law of thermodynamics. And this is a problem that starts somewhat easy. I reckon the first four letters are somewhat easy, and then it ends up a bit harder on the last letter. The problem statement reads: nitrogen gas with a molecular weight of 28 grams per mole and a K of 1.4 flows steadily through a constant area pipe. The gas enters a pipe at 3.5 megapascals, 60 degrees Celsius, and a velocity of 10 meters per second, and a volume flow rate of 4.52 meters cubed per hour. At the exit of the pipe, the pressure is 0.2 megapascals, and the temperature is 50 degrees Celsius. Determine the cross-sectional area of the pipe, the mass flow rate, the volume flow rate at the exit velocity of the gas, and the rate of heat transfer to the nitrogen in the pipe. So before we jump, let's do a little problem analysis. We're talking about nitrogen gas, so we're not going to be using steam tables. Obviously, it's not steam. Property tables will most likely not be needed because it's an ideal gas, right? So first thing you want to write down, it's ideal gas. So, remember PV equals nRT, and all those relationships are valid and will probably be useful. Next up, K of 1.4. What is K? If you don't remember, K is actually the C sub P divided by the C sub V. And these guys, the definition is the way the enthalpy varies with temperature and the way the internal energy varies with temperature. Okay, just to remind you, definition. It flows straight, constant area. This is also important. This is a constant area pipe, so therefore the area in the inlet is the same as the area in the outlet. Okay, and note that there is a change in temperature. Okay, we're going to get to that. The gas enters the pipe at velocity, volume flow rate. Another thing to be aware of, this is a strange unit, right? So whenever we see something off, this is per hour, not per second. I recommend you marking it down because it's easy to forget about it and it comes back to bite you later. At the exit of the pipe, pressure is and temperature is 50. Okay, so note that we're going from 60 to 50, right? We're decreasing the temperature, and I'll call your attention in a second why that's relevant. We are to find the cross-sectional area of the pipe. So the cross-sectional area is, on this image that I drew down here, is this area here. Okay, that's a cross-sectional area. So obviously we're looking for something like meters squared or any other units of area. Mass flow rate, we're looking for the units of kilograms per second or per hour or something like that. Volume flow rate at the exit, so the same volume flow rate here, so we can do it in meters cubed per hour or meters cubed per second. Doesn't matter, whatever rocks your boat, whatever's easier. The exit velocity of the gas, so meters per second here. And finally, the rate of heat transfer to the nitrogen, and this is rate of heat is joules per second, which is given in watts. Okay. There's the answers are down here, so we can use that to our advantage, right? So you want it millimeters squared, kilograms per hour, meters cubed per hour, meters per second, and watts. So this is more kilograms per hour. Okay, what is relevant here? Note that this is saying the rate of energy transferred to the nitrogen. This is super counterintuitive if you're paying attention. Why? Because as I pointed out before, the temperature is decreasing, right? Temperature is decreasing. So going from 60 on the inlet, 60 on the inlet down to 50 on the outlet. If this is where all that was happening, we were sure that we'd have energy be leaving this nitrogen gas as it's going through the pipe. So it strikes me as odd that this is to the nitrogen, so we need to observe if that makes sense at the end of it. Okay, so let's get started. I wrote down the properties. This is the inlet over here. This is the outlet over here. I wrote down the properties that we were given. I'm going to go ahead and start with the idea that the cross-sectional area okay, is, like I said, this area here is going to be the same on the inlet or the outlet, so it doesn't matter. So I'm going to go ahead and use the properties of the inlet because I have more properties there to calculate it. And I'm going to relate the cross-sectional area with the volumetric flow rate, because if what we know is that if there's a certain velocity going through a certain area, that velocity meters squared times the meters squared of the area times the meters per second of the velocity is going to give me a volumetric flow rate. So if I multiply velocity and cross-sectional area, I get a volumetric flow rate. Surprise, surprise, I have a volumetric flow rate, so I can use that to my advantage. The other thing to be aware of is that if I want to find out what is the mass flow rate, I can relate this volumetric flow rate to the mass flow rate by using the idea of specific volume, right, which is just the volume divided by the mass. So if that's true, and this specific volume is a constant, I can say that the rate of volumetric flow rate, which is the mass flow rate, times the specific volume. Okay, so what I'm saying here is, you don't need to remember this by heart, but what I'm saying is, if I were to derive both of these terms in respect to time, I'm going to get the volumetric flow rate over here, I'm going to get the mass flow rate over here, and this is a constant, doesn't care about time, it just comes out of the integral on the inlet anyways, or the outlet, or whatever place inside that we choose to do this analysis. Okay, so part A, what is the cross-sectional area? Well, the cross-sectional area will simply be the volumetric flow rate divided by the velocity. Volumetric flow rate is 4.52, and we're dividing that by the 10 meters per second of the inlet. But when I look at the unit here, I'm going to note that I have meters cubed per hour, and down here, meters per second. If I'm looking for a cross-sectional area, I will end up with meters squared times seconds divided by hours, so that's not good enough. I'm going to have to put another term here to be able to cancel out these seconds and these hours, and then that's easy. 1 hour is the same thing as 3,600 seconds, and with that, I can go ahead and cancel hours and hours, seconds and seconds, so I just need to ensure I'm dividing by 3,600 there, which gives me an area of 1.256, and that time 10 to the minus 4, and that is meters squared. So we can stop here if we want and call this our answer, or we can go ahead and convert that into millimeters to have the answer that they want. And that's 125.6 millimeters squared. Okay, so that's going to be times 10 to the 6, which eliminates this here, and then 2 puts it 125. All right, so that's obviously the same answer. That's part A. All right, part B. What is part B? What is the mass flow rate? What is the mass flow rate? So we can use this idea here for the mass flow rate. That's straightforward, but we don't know the specific volume, at least not just yet. What we do know is that this is a ideal gas, so it needs to respect the ideal gas relationship. And we know that the volumetric specific volume is just volume divided by mass. So I can make that happen by dividing the whole thing by the mass. So I'm going to have this equation as PV over M equals RT. Guess what? This is specific volume, so it's the same thing as pressure specific volume. So if I want to find a specific volume, which is what I'm after here, I can just do R divided by T times T divided by pressure. Why would I want that? Well, because then, as we noted here, I'm able of calculating the mass flow rate by relating the volumetric flow rate and dividing that by the specific volume. So over here, what I need to do is place the R and the T. There's one small caveat here though. Note that we are looking for the specific volume. So it's a unit that is in meters cubed per kilogram. If I go ahead and place 8.314, I'm going to have a problem because this is kilojoules per mole per Kelvin. Okay, so this is no good for me. What I can do, right, to overcome that is relate the 28 grams I was given before. Right? I was given that the specific the molecular weight of nitrogen is 28 grams per mole, so I can use that to my advantage and therefore not worry about this. So that's what I'm going to do. I'm just going to place the values here. So our temperature is on the inlet is, what is it? 6333 Kelvin. 333 Kelvin. And our pressure on the inlet is, I forget everything, sorry. 3.5 megapascal, 3.5 times 10 to the third kilopascals. 3.5 times 10 to the third kilopascals. And as noted, our units will be kilojoules per Kelvin mole. That's for R. Then we have Kelvin on the temperature, and then we have kilopascals. Pascals on the bottom, right? So we converted megapascals into kilopascals. We put in the 3 there. Brilliant. We also need to eliminate that mole, and therefore what I'm going to do is go ahead and multiply the whole thing by 28. That's grams, so 10 raised to 10 to the minus 3. That's kilograms per mole. Okay, so we have that amount per mole. And then what happens is, let me just keep this in green. So we have everything in green. Kilograms per, oh, that's not going to work. This will work. Okay, so kilograms per mole. And then moles and moles, kelvins and kelvins, kilo and kilo. We get joules divided by pascals, and we know this is going to be meters cubed. So we get meters cubed per kilogram, which is great because we're after a specific volume. Okay, so we can do that, the whole thing, to get the specific volume. And what I got here out of this is 28.25 times 10 to the minus 3. And that is in meters cubed per kilograms. Okay. What else do we need here? My mistake. This guy here, 8.3, that's joules, not kilojoules. That's joules per Kelvin per mole. So we still have that kilo there. And because of that kilo, I need to remove that kilo. And then for that kilo, I need to do another step here, which is to say that 1 kilojoule is the same thing as 1,000 joules. And there, that's what I need in that last piece of the puzzle. And then I can remove the kilo, and then this Pascal removes this joule. And then I can be left with meters cubed. Okay, so that's where the minus 3 comes in. Because if it were just these two, they would just eliminate each other. Okay, we're good. All right, what else? What are we after? We're after the mass flow rate. We got the specific volume. Okay, we're good. After the rates is now. So this is the volumetric flow rate that we happen to know is 4.52. And we have the specific volume, which we happen to know is 28.25 times 10 to the minus 3. This is meters cubed per hour. And then here is meters cubed per kilograms. So that will give me kilograms per hour, which is just fine. And we can keep it that way. And that's going to give us 160 kilograms per hour. And that's all good. And that's a good answer too. If we want, we can also convert this into kilograms per second. And that will be 4.444 times 10 to the minus 2 kilograms per second. Okay, whatever, actually, both are correct. All right, moving on.